Thanks to Mike and the organizers for putting this on and for inviting me. I always enjoy being here. So I was setting out to make this talk, and I realize now that I had in mind some more general work than what I'm actually going to tell you about, because I have in general been interested in this problem, and I'll be happy to talk about the more general non-convex optimization problem. This talk ends up being about one specific problem, which I'll get to. But before I do that, I want to acknowledge my collaborators. Shenyang Yi is a PhD student at UT. Yudong Chen is now at Cornell as an assistant professor. He was at UT, then he was at Berkeley as a postdoc. And Do-Young Park is also a PhD student at UT. So this does tie in actually to Alex's talk, which I gave about an hour ago, and this idea of non-convex, the importance of non-convexity in high-dimensional problems. So, something that many people here have worked on, and many people elsewhere have worked on, is this problem in high-dimensional statistics. And the success story here has been in our collective ability to find techniques that identify some simple structure that's nonlinear. When I say nonlinear, I mean we're not just finding, it's not that we're projecting onto one specific low-dimensional manifold. It's something else like sparsity or low rank. And it's basically this simplicity, this simple structure that has some kind of low intrinsic dimension, which is what allows us to get around this high-dimensional statistics problem that we have many more degrees of freedom than observation. So there's many examples of this which I think are familiar to many people here. So sparse regression, of course, is the example par excellence of this type of problems, but also looking at, we've already heard some talks in the previous session on low rank matrix solution. Related to that is low rank matrix completion. The problem actually that this talk is going to focus on is the fourth bullet. It's recovering a low rank matrix that's been perturbed by erasures and by sparse corruptions. And there's many different problems here. And what's enabled us to solve these, to a large extent, what's enabled us to solve these hard problems is that we've understood pretty well this idea of convex optimization and algorithms for solving fairly large problems in convex optimization. So f of x is a convex function, script x is a convex set. And the key insight that's allowed us to leverage these tools is that while the original problems I put on, sparse regression, and so on, are non-convex, their solutions are often, at least approximately, solutions to convex problems. So, I'm getting a bit excited. So the general paradigm has been find a convex problem whose solution is very close to the problem the non-convex problem that you're hoping to solve. Okay, so the problem that I want to focus on in this talk is the following very specific one. I would like to recover a low-rank matrix L, but I don't get to see the matrix L. What I really get to see is a low-rank matrix L with a lot of sparse and arbitrary corruptions. So I get to see Y. Or maybe I get to see a partial observation of Y. Okay, so this is my problem. And several years ago, Venkat Chandrasekaran and Sujit Sanghavi, Pablo Perillo, and Alan Wilsky, and also Candace, Yi Ma, John Wright, and Lee. Sorry, I forget the first name, but I got into a pattern of saying everyone's name. All about at the same time, looked at this problem and did realized the following thing, that if you minimize this convex objective where lower star indicates the sum of the singular values, and 1 is the usual L1 norm but applied to a matrix. So if you minimize this, these first two elements, the first one is basically a convex proxy that encourages low rank. The second one is something that encourages sparsity. So if you minimize this objective, subject to the fact that they're consistent with the data that you observe, then under some conditions, this has great properties in the sense that we're able to recover L star. So, I mean, now I think this is old news for many of us, so we've forgotten how amazing it was initially that we could do this. And the results basically say that if S, the perturbations are placed randomly, even though their values may be arbitrary, then we can recover from a huge number, a constant fraction. And if they're placed in a perhaps adversarial way, these perturbations, then we can recover from a slightly smaller fraction, 1 over R, where R is throughout the talk going to be the rank of this low rank matrix. So the more low rank you are, the more perturbations you can endure. So this is great. And convex optimization is able to solve it. So shouldn't this be enough for us? But no, we're never satisfied. But why aren't we satisfied? Because we want to solve larger problems, and SDPs are typically very difficult to solve. So what should we really ask for? What might we hope for in terms of computation? So just to read in the data, unless you have a lot of sparsity, so just to read in a generic problem, you need order D squared, where D is the size of the matrix. This all extends to rectangular as well, but just to simplify notation, I'm thinking about a D by D matrix. So you have D squared elements that you're shown, you at least need to do that much work. If you want to write the solution, a rank R matrix, you need at least R times D, order RD. Okay, so that's better than D squared. And if you just wanted to solve the PCA problem and you had no further assumptions, then you would probably do a rank R SVD and take order R D squared time. So what I'd like to know is, now that I have this, of course we know that if we try to do SVD and we have these if we have these arbitrary corruptions, we'll do extremely poorly. So what is the additional price that we need to pay in order to, over SVD, which is somehow the minimal thing that we could do without anything more fancy, in order to be able to deal with these corruptions? So if you want to solve the SDP, which was the original solution, that objective function there is SDP representable, you need to pay quite a bit. You need to pay, I think D to the fourth is probably quite generous to say that SDP runs in that much time. A few years ago, Lin, Chen, and Ma developed an inexact augmented Lagrangian multiplier method that was able to run in order D cubed time. I should also note that I've kind of suppressed, I'm just showing dependence in the dimension. I've suppressed dependence on things like incoherence and error and so on. So I have some of these later, and they're also in the paper. So I'm just really focusing on dependence on R and D. And then Netrapali, Sanghavi, and Jain, and Anand Kumar a few years ago looked at a non-convex approach for solving this convex problem. And they significantly reduced the complexity from D cubed to R squared D squared, which is getting pretty close to SDP, to SVD. So the SVD cost would just be RD squared. So they got R squared D squared. And what their solution called alternating projection, what it basically did is it subtracted out the big elements, that put them in the sparse set, and then did an SVD of the remainder, and then repeated. So it basically did repeated SVD back and forth. So it was alternating projection onto a sparse component, alternating and then projecting onto a low rank component. Okay, but so these I would characterize as convex. The first two are convex approaches for solving a convex problem. And then the last bullet, which has the best running time of the three, is a non-convex approach, but still for solving this convex optimization problem. So we thought we would take a different path. And actually, rather than have something that encourages us to be low rank, let's force it to be low rank. So this is a trend that people have been using for some time as a heuristic, and recently for some problems has been analyzed and given some rigorous guarantees. But this is the problem that I'm thinking about. So S is as before, it's a sparse component. Y is again as before the data that you're given, And now instead of having an L that I want to push towards being low rank, I'm going to minimize over U and V that are tall and thin matrices. Okay, so I'm actually forcing low rank, and therefore that doesn't need to appear anywhere in the objective. So the low rank output is guaranteed for any solution of this problem. The quality is what we're curious about. So there's many advantages, of course. First of all, you don't have to store, you don't have to manipulate D by D matrices. You just have to keep these D by R matrices U and V, and hopefully F is sparse. And of course, the price we pay is that this is now bilinear, and in particular, it's not convex. So it's convex in U by itself, or in V by itself, but not in U and V simultaneously. So this is a problem. So we want to understand when can we guarantee that essentially the obvious thing that you would think about, when is that going to work? So what is the obvious thing? Well, there's something that may not be that obvious, which is how we initialize. So I'll get to that in a second. That's quite important. But the kind of obvious thing, since we know about convex optimization, is that if I have something that's convex in U and something that's convex in V, then let me just do gradient descent individually on U and V and try to understand when this idea works. So what is the cost? So the cost is no longer doing an SVD at every iteration, which is what was the cost in the previous best running time solution, which I mentioned was R squared D squared. So they have to do an SVD at every iteration. In this case, the main cost of doing gradient descent is going to be this UV matrix multiplication, because that features in the gradient calculation. So at every iteration, I'm multiplying RD by an RD matrix. So it's not surprising that if you can show that not too many iterations are needed to converge, you get the following result. That for R, again, the rank, if it's big, then you get RD squared. Actually, if it's small, you get RD squared. But the second bullet says that if it's small, you might want to choose a different approach. So this first bullet says that we're able to reduce the complexity from R squared D squared, which is the previous best, to RD squared, which is essentially the cost of doing a single SVD. So that would be the cost of solving the problem if you had no corruptions. Now, if you have a very low rank problem, very low rank compared to the dimension, you can actually reduce the dependence on D to almost linear in D. So for a really low rank problem, this problem now becomes just linear in D. If you have, say, order 1 rank in particular, that would be, you have a much faster. And so this also works even if you have many erasures on top of the model that I've said. And I wrote because that's actually the key from getting from the first bullet to the second bullet. If you have very low rank, you can actually on purpose delete most of your elements and really greatly speed up your computation, and then we can show that things still work. So let me tell you an application of this that we played around with a little bit. And this is this problem of separating foreground from background in a video. So the approach is, we have the video here of me talking and I'm waving my arms and walking around, where the background is more or less staying fixed. I mean, I occasionally change the slides. So if you were to take the frames of that video and just stack them as columns in a matrix, then there is a low rank component and there's a sparse component. The low rank component is the background, because that is the same thing in every single slide. It's a rank 1 component, in fact, if I stack every frame as one column. I'm moving around, so I'm the sparse. If you think about this matrix with the columns indexed by time, then I'm the sparse perturbation. Okay, so we can try to apply this and recover the results. And I made a little video of this to show you how this works. You may have seen, this is a standard video. This is the original. Does it show? Yeah, so this is a surveillance of a restaurant scene. And the background is the counters and floors, and then the sparse perturbation is the people moving around. In this particular application, there's no real motivation for subsampling, but just for fun, I'll just show you what it looks like when it's subsampled. So the task is from this to figure out what the background is. Okay, so this just looks a bit fancier. But I mean, obviously for this application, I don't think we really need this. So let me show you how we do. So when we run, so this is what we get as the background when we run this gradient descent on the sampled version. Okay, so you definitely see some artifacts there, but it's basically stripped away all the people. And I want to also note that I didn't play the whole video because it's about 1.5 minutes, but there's no frame in the original video that shows the entire background by itself. So there's always some part of the background that's obscured in the original video. And I also want to mention that the algorithm we run is exactly what I showed you. We don't use anything about edge detection, no insights from computer vision, because I have no insights from computer vision. So this is just running exactly what I showed you. Just to poke my colleague Sujay, who did the alt proj, I want to show you how he did, and you can see some more people pop up here. So this is recorded, so I won't say too much because we're neighbors. But yeah, so this is the alternating projection, which is also more expensive in terms of computation time. So the point is that for this application, this is successful. But the most thing, I mean, this is an interesting application. I wouldn't say that it is our motivating application. Our motivation here is to understand how these non-convex methods work and what conditions we really need. But I do want to show you, I think you can see it here, that there are really significant improvements in running time. The top is what I showed you. It's the restaurant scene. There's a very similar surveillance from a shopping mall. And I just extracted some frames here. But the key thing I want to point out is the running time for this whole procedure. So the movie is about the restaurant is about 100 seconds long, and I didn't even do STP, but this inexact augmented Lagrangian approach takes about 5 times longer than the movie. Alternating projection, which alternates between stripping off the biggest elements and then doing an SVD, takes about as long as the movie. Our method on full observations is about twice as fast, and then about 5 times as fast as that when we subsample, even though the quality is essentially unaltered. So what we did here is, on purpose, we just threw away 80% of the samples, and that greatly speeds things up. And this is kind of a common trend also in the second surveillance, in the second movie thing, and we also simulated this on just synthetic data, and also we found speed ups that were quite considerable. So I think that this, while our target is not this type of, while our motivating application is not this kind of surveillance application, I do think that these types of things are interesting because in many devices, sensing has really outpaced computation, storage, and communication. So if you think about your iPhone, it can very, very quickly record HD video that exhausts its ability to communicate, to do computations with, or to store. So I mean, in that sense, there are many such settings where if you want to do some kind of learning on the platform, you want to do something that's really lightweight. Okay, so this is just going over the running time, which I just mentioned. Okay, so there's quite a considerable, from the convex optimization on top, 400 plus seconds down to 18 is a considerable speed up. But even from 100 seconds down to 18 for very similar quality is, or possibly even slightly better quality is a great speed up. So this idea of, as I mentioned, of working in the factored regime is not new and has been used in a few different areas. I'm citing the work that I'm aware of that has theoretical guarantees. As a general way to speed up computation, this has been around for a very long time. There have been some alternating minimization approaches for low rank recovery and for matrix completion. And I'm sorry if I've left out some people, but these are the works that are probably most comparable to ours. But there's a lot of others, and so in contrast to the previous work on inexact augmented Lagrangian or the alternating projection, these have much faster running times, but they have no robustness guarantees. So if you take any of these problems that basically do low rank matrix recovery and you add arbitrary and sparse corruptions, they completely break down. So that's really the area that we're trying to understand. There's some additional challenges in that we're not assuming anything about positive semi-definiteness or symmetry, which previous work has assumed. So I want to tell you a bit of the results and some of the intuition about where they come from and what are the kind of conditions that you need. So again, just to remind you some of the notation, L is my low rank matrix and R is its rank. We have some parameters that I haven't talked about but appear in all the work in these types of applications, not just in these types of algorithms, namely how well aligned the singular vectors are with the standard coordinates. And this is something called the incoherence, which I denote by mu. And then the standard condition number, L is low rank, so when I talk about the condition number, I'm talking about the largest to the smallest non-zero singular value. So I'll point out where these come up. But they're pretty much standard, the kind of dependence that we'll see. And again, the corruptions that we have are arbitrary and arbitrarily positioned, except for a sparsity constraint. So there's a limit to how many corruptions you can have on any row or column. So in that way, they're somewhat forced to be spread out. But other than that, we don't make any assumptions about where they are or what their values are. Okay, so this is a bit of a dense slide, but it's not too bad, and it really describes what the algorithm is. So that first equation up top is basically saying what we're trying to minimize, and I wrote that down before, or I wrote down something very similar. So the first expression there, uv plus s minus y, that's just how far you are from matching the data that you saw. S is your sparse component, uv is your low rank component. You'd like uv plus s to be exactly what you saw, and you get penalized for not having that exact thing. The second term there is something that we actually need, and we need it because the problem is not symmetric. So because it's not symmetric, the left and right eigenvectors are different, and we need to make sure that they're balanced, and essentially that's what this last component is doing. So yeah, I didn't know how to get away with doing less notation, but I think I can talk through what this is, what the initialization is, because it's quite simple. The initialization is basically selecting the biggest components from Y. So whatever, you take the biggest components that you observe and you say, this is my guess for what the sparse component is, and then you initialize by doing one SVD, and that's the last SVD that you're going to do, of whatever remains, Y minus that initialization. And then this last thing is exactly what it says. You just keep doing gradient iterations and then truncating. So you basically do this initialization and then just do gradient iterations of that objective with the sum of the two Frobenius terms. So when would we expect this to work? So we need two kinds of conditions, which are very natural if you think about it. So first of all, you'd like, since you're doing gradient descent, just like with convex optimization, if you're far from the optimal, you want it to be steep. You don't want to be far from the optimal and be in a very flat region, otherwise gradient descent is a terrible idea. But on the other hand, you also want smoothness, which means that when you get close to the optimal solution, things do get flat. And the reason you want that is so that you don't overshoot. If you don't have this property of smoothness, then you have to take tiny step sizes. And if you're going to take tiny step sizes, it means it's going to take you a very long time to get to the optimal solution. So if you think back to basic first-order methods for convex optimization, you really need both of these conditions if you hope to have some kind of linear convergence. Whenever you take away smoothness, even if you have strong convexity, then you basically lose, you only have sublinear convergence. Okay, so a consequence of these things is that when you're far away, things are very steep, and we can afford to take really big step sizes. We don't have to take step sizes proportional to the error we hope to achieve. Okay, so this is another dense slide, but I wanted to explain where these two things kick in. And basically, if you think back to the kind of standard way that you would prove rates of convergence for gradient descent, really all this is, the first line is my loss. How far is u from the optimal? How far is v from the optimal at iteration t plus 1? You can write this as a recursion of how far ut is from optimal plus vt is from optimal plus some other stuff. So what this other stuff is doesn't typically appear in this form in a standard convex optimization problem. It's w1 plus w2 plus w3 plus w4. And note that w1 and w2 have a minus sign. So we want these to be big. For these to be big, this is what the descent condition is guaranteeing. It's basically saying that the gradient is steep if I'm far away from the optimal solution. On the other hand, you want w3 and w4 have positive signs, so I want these to be small. And what are w3 and w4? They're gradients. So you want that to be small when you're close to the optimal solution. Okay, so I know this is a bit of a thing to parse here, but I wanted to show you where do those two conditions of descent and smoothness really come in. So the basic framework is that requires showing a few things. So first of all, initialization. Showing that our initialization step, that all true optimal solutions end up being close to the initialization. And also, the initialization is good enough to guarantee that you have the descent condition and the smoothness condition that I mentioned. And there's several key technical challenges. Definitely, it's in establishing these local descent and smoothness conditions. And I want to point out that this is unfortunately is not a generic agenda yet. I think it's an area that I'm quite interested in, and I think many people are working on this, but it's still at the level that we need to use specific problems and structure of the problem at hand to establish these types of properties and to do it carefully. So for example, when we move from, and I'm going to show what the exact theorems are in a second, but when we move from full observation to partial observation, our step size can no longer be proportional to just 1 over smoothness. We also have this additional factor of mu r in the denominator. And basically this comes from the fact that it comes from the structure of the problem that we have to control the size of projections onto sparse supports. So it's a bit delicate still at the level of showing these local descent and smoothness conditions. I guess I'm conflicted myself in the way I'm saying it. I mean, on the one hand, that's kind of the contribution of the work. On the other, I think it's important to realize that we want an understanding that's broader than any particular problem structure. Okay, so my time is running out. I just want to, so the basic theorem says that you have linear convergence at exactly the kind of rate that you would expect from a convex problem. And so the running time is essentially log 1 over epsilon times the cost of every iteration, which is RD squared. And if you compare that with basic SVD, SVD would take RD squared already. For partial observations, you have to, again, there's a lot of notation here. You have to slow down your step size quite a bit, but the key takeaway from this slide is that, again, you have linear convergence, and the amount of, and also that you can tolerate as many corruptions as you could before. So even when you have partial observations, it comes at no cost to your robustness guarantees. So in summary, this is an approach that's really much faster than convex or even other approaches that we're aware of. But I really think the name of the game in these types of problems is understanding how the initialization fits in. Efficient initialization techniques work with the kind of conditions you need to guarantee things like local descent and local smoothness. So, thank you.